And so let's take an example. If we use forward order to solve, let's look at equation 1, right? Forward order for equation 1. We would have m times un plus 1 minus un divided by delta t equal to minus kappa times a un plus b. Okay. Here, in order to solve for this un plus 1, we have to have un plus 1 would have to be equal to what? M inverse, right? Times something. M inverse times, well, m times un, so that's this term, and minus delta t times kappa a un plus delta t times b, right? So that's forward order. You have to invert this matrix M. All right. If you apply backward order also for 1, that's an implicit scheme with all the advantages of implicit scheme. You would have m times un minus 1 delta t equal to minus kappa, the same thing here on the right hand side. Okay, so the unknown here is un and un on the right hand side. So normally that means you would have to invert a matrix even if the forward order doesn't have to invert a matrix. But here you have to invert a matrix anyway. And using backward order wouldn't actually require you to invert any more than if it wouldn't require you to invert the matrix once. You just invert a different matrix still once, right? So if you look at the left hand side, what you have is m divided by delta t, so that's here, and you lump in the right hand side plus a kappa a, so that whole thing times my unknown un would then equal to the known part of the equation, m over delta t times un minus 1 plus b, right? So instead of inverting the M matrix, you invert this matrix. So essentially the cost is going to be similar, and you gain advantage of implicit integration. So this is something a little bit unique for finite element method for discretizing partial differential equations. All right. Any questions for this part? No? Okay, so let's actually spend a very quick few minutes on using finite elements to solve equations with first order derivatives. Okay, I'm not going to say much, but like since you have to do this in your project, I'm just going to really quickly go over it. So first order derivative, first of all, is actually there are a lot of different techniques to treat in finite elements. But for our purpose, for the purpose of the project, when you have an equation that is dominated by the second order derivative, it's actually okay to treat the first order derivative pretty much the same way as we treat the second order derivatives, like using the same Galerkin type of method, using basically the same space for the test function v as we use for the solution u. So if we have a bunch of terms with du dx equal to a bunch of terms, right? So I don't care what it is. Again, if you do finite elements, you multiply the whole equation by a test function v. So you have the other terms multiplied by v plus this first order derivative term plus v, right? Equal to, again, everything is multiplied by v. And you have all the things integrated over the domain plus this term integrated over the domain, right? So that is basically zooming in, focusing on just the first order derivative term. And now, again, you choose u to be Well, here you have an option of doing integration by parts or not doing integration by parts, right? So if we don't perform integration by parts, then we have u inside the derivative and v outside. If we perform the integration by parts, we would have u out of the derivative, but v now inside the derivative. So it doesn't really gain us anything in terms of having like basically either u or v has to be differentiable. And if we have to be if we have a second derivative anyway, that kind of dominates the differentiability. So here is it doesn't really matter that much. So here we have u equal to ui, and the ui would be a number, unknown number, if we don't have time derivative, or it's just a function of time if we do have time derivative. But the phi is going to be strictly a function of x, okay? And then v is equal to phi j, where j goes from 1 to n, all right? And this n might be changed to n minus 1, and the I equal to 1 may go from I equal to 0 if you have different boundary conditions. So after this, we still have all these things changed, but here is going to be the particular first derivative term is going to be now phi j times a summation of over I of now ui is going to be not a function of space, so the differential operator doesn't work on it, and the phi is going to be a function of space, so it is differentiated, right? Okay, and this gets you a term like this. We pull this summation over I out of the integral, and ui being not a function of space also can be pulled out of the integral, and we have something that's like phi j times derivative of phi with respect to x. Now what we have here is yet another matrix, right? This is something you might call bij, right? That deals with the first order derivatives. Okay, so what we have done is that basically any a different operator, for example, involving a first order derivative, can be gone through the same kind of finite element procedure, and we just pull out another matrix that is a representation of the first order derivative. So essentially at the end, you're going to get a lot other terms plus this B matrix times the U vector equal to other terms, right? The other terms may involve the stiffness matrix, the mass matrix, and things like that. All right. Okay, so this is really the extent to which we are discussing how do we apply finite element method to different equations. All right, I want to see if there are any questions up to this point. Yeah, no questions, not even in chat.